Okay, so in this video, we want to consider the concept of linear combinations. So what is a linear combination? And here we'll do it in full generality in Rn for any given n. So take m vectors, say v1, v2 up to vm in Rn, and from now on, when we consider Rn, the n-dimensional space, we will always think of the vectors as column matrices of length n, therefore with n entries. So never again as a n tuple of real numbers, but as a column matrix of length n. So suppose you have m vectors, v1 through vm, in Rn, therefore column matrices of length n, and take m real numbers c1 through cm. An expression, so then we'll define what a linear combination is, an expression of the form well, what is the expression? It's some scalar multiple of v1, so c1 times v1, plus some multiple of v2 up to some multiple of the mth vector vm. An expression of this form is called a linear combination. A linear combination and there are two key sets of things here. There are the vectors v1 through vm and the scalar multiples c1, c2 through cm. So this is called a linear combination in the vectors, so in or of the vectors, same thing. Linear combination in or of the vectors v1, v2 through vm, I should say actually a linear combination simply of. This is called a linear combination of the vectors v1, v2 through vm, and in the coefficients c1, c2 through cm. And that's all a linear combination is. Take m vectors in Rn, take m real numbers, and if you do c1 times v1 plus c2 times v2 up to cm times vm, we call this a linear combination of the vectors v1 through vm in the coefficients c1, c2 through cm. A natural question from this, and you'll see as we look at new concepts and at different objects and spaces, we'll always try and simplify as much as we can the structures we're dealing with. And the idea will be, with a given set of vectors, what are the things that we can generate from these sets of vectors? So a natural question to ask, and this is what a linear combination is, if you fix the m vectors v1 through vm, a natural question to ask is, well, what other vectors can you obtain as you vary the coefficients over all real numbers? Let's consider a simple problem, and then this will hopefully be a very familiar problem indeed. So suppose that we have another vector u in Rn. One question that is natural, and you'll see over and over again in the following sets of problems, is we're going to ask, is it possible to obtain vector u, to express vector u as a linear combination of these m vectors? So imagine that you fix these m vectors and you ask, given another vector u in Rn, can you obtain this vector through a linear combination of these m vectors? So by choosing the coefficients carefully, will you be able to express u as c1 times v1 plus c2 times v2 up to cm times vm? Now think of how you would solve for the coefficients. The vectors v1 through vm are fixed vectors, so is the vector u. The coefficients are the unknowns. Let's see how we can rewrite this in a hopefully very familiar form. So we ask, is it possible to express the vector u as a combination of these m vectors? So c1 v1 plus c2 v2 up to cm vm. Can we choose these m coefficients so that the end result, the linear combination, is equal to vector u? And now think of it. From now on, as we've said in the intro of this video, we will only think of Rn as the set of column matrices of length n. So let's write this here. And let's think of the implications of that. So Rn for us is the set of column matrices of length n. Oops. Rn, not R2, but Rn for any n. So x1, x2 up to the nth component of our column matrix, where again the xi's are any real numbers. That's what Rn is. Let me rewrite it here. So the set of all column matrices of length n, with n components, x1, x2 through xn. That is what Rn is. So now think of this equation. Now think of combining the sum of these m vectors into a single vector, and think of the first entry of the vector. You would have c1 times the first entry of v1 plus c2 times the first entry of v2 up to plus cm times the first entry of vm equals the first entry of u. Well, that would be a linear equation and the coefficients c1, c2 through cm, where the constant term is the first entry of vector u. And now look at your second equation. If you pick the second row of this vector, you would have c1 times the second entry of v1 plus c2 times the second entry of v2 up to cm times the second entry of vm equals the second entry of vector u. And if you do this for all n entries, what you will get is a linear system. And if you build the augmented matrix, here's what it will look like. The c's are the variables, the things you're trying to solve for. This would be c1, c2, cm. The constant terms are given by the entries of vector u, and u again is a column matrix, and the entries multiplying c1 are the entries in v1, so v1 will be the first column of our matrix. The entries multiplying c2 are the entries of v2, so v2 is the second column of our matrix, up to, of course, vm, because the entries of vm are multiplying cm. And you see that solving this equation, so finding coefficients c1, c2 through cm so that u is a linear combination of the vectors v1 through vm, amounts to solving the linear system where the coefficients are the variables, the vector u is the vector of constants, and the columns of your matrix are simply the column vectors corresponding to each coefficient of the linear combination. You could also, if you wanted to, rewrite this, as you know, as a matrix equality, whichever one is more convenient. So this is the matrix whose columns are the m vectors in the linear combination, so v1, v2, through Vm times the vector of variables C1 through Cm times the column vector C1, C2 through Cm, and this equals the column vector U. So two ways of rearranging the linear combination of the vectors v1 through vm equaling vector u as the linear system with the augmented matrix form, or has a matrix equality. The matrix where the columns are built with the vectors from the linear combination, the column of variables containing the coefficients, and the constant vector being the vector u. So every time you ask, is a vector expressible as a linear combination of m vectors, to solve for the coefficients, just build the augmented matrix and then we'll reduce and solve for the coefficients. If it is more convenient, you can also use the matrix equality. This matrix times this one equals this one. We can give this matrix a name. We can call this matrix, say, A. Let's do a simple example with vectors in R2. And again, whether you're in R2, R3, or beyond, the only difference is you'll have more equations, so it's slightly bigger linear systems, but by now we can reduce any linear system. So let's do an example. And of course, one thing which is obvious from our conclusion that we have to solve a linear system, sometimes we will have no solution. So it is possible that expressing u as a linear combination of m fixed vectors cannot be done, and this will translate into an inconsistent linear system. So we'll always say, if possible, express the vector u, and we'll take a vector in R2 just to make the calculations shorter. So the vector is -3, 7. So if possible, express this vector as a linear combination of the vectors v1, say. Let's take a vector 1, 2, and v2. Let's take -1, 4. So here's the problem. If possible, express the vector u as a linear combination of these two vectors. Well, let's go back to the definition. We're asking, can we find a coefficient c1 times vector v1, so a multiple of v1, plus another multiple of v2, so that if we choose the coefficients c1 and c2 properly, we will get vector u. Therefore, expressing vector u as a linear combination of the vectors v1 and v2. Well, we know how we can rearrange this linear combination as a linear system. And let's just, for now, check that we're okay. But later on, you don't have to check this again. But let's compute c1 times v1. This will give you the vector c1 to c1, plus c2 times v2 will give you the vector -c2 for c2. If you add those two vectors up, you will get c1 minus c2 as the first entry, 2c1 plus 4c2 as the second entry. And this would have to be equal to the vector u, which is -3, +7. And if you look now, by collapsing this linear combination into a single vector, you have a vector equality or a matrix equality. Therefore, corresponding entries must be equal. So C1 minus C2 must be equal to -3. And 2C1 plus 4C2 must equal +7. And you see that we have reduced the problem of expressing U as a combination of V1 and V2 to solving a simple linear system. Let's rewrite the augmented matrix and notice that, as we have claimed, the constant column will be formed by U, and C1 and C2 will be the unknowns, and the coefficient matrix will be built by V1 and V2. The variables are C1 and C2. Multiples of C1 are 1 and 2. Multiples of C2 are -1, 4. And the constant term is -3, 7. And as we have claimed, if you look at this, the augmented matrix, the first column of our matrix is the first vector V1, right? If you go up, V1 was 1, 2, 1, 2. The second column of our matrix was -1, 4, which indeed is V2. So C2, V2, V2, -1, 4, being equal to the constants -3, 7, and these are the coordinates of vector U. And this will always happen. So we just checked here by combining this combination as a single vector, equating corresponding entries. We have the system, we write the augmented matrix, but you can always avoid doing this and jump straight to the augmented matrix. The columns of the coefficient matrix are the vectors v1 through vm. Here we only had 2. The column of constants is the vector you're trying to express as a linear combination, and of course the variables are the coefficients. Let's row reduce, and then we'll have our linear combination, of course, if possible. Let's do row 2 minus 2, row 1. So we'll get 0. This is our first leading 1. 4, -2 times -1 is 4 plus 2, 6. 7, -2 times -3 is plus 6, 13. Divide across by 6 to have your second leading 1. You'll get 0, 1, and 13 over 6. Finally, let's get the reduced row echelon form. Let's do row 1 plus row 2. Recopy row 2 as we're not changing it. The matrix A becomes I, and we did -3 plus 13 over 6. Well, -3 over, if we put this over 6, will be -18 over 6. -18 plus 13, -5 over 6. And now we have the value for the two coefficients. We have a unique solution. Coefficient 1 is -5 over 6. Coefficient 2 is 13 over 6. So our conclusion is that vector u is equal to -5 over 6 v1 plus 13 over 6 of v2. Let us check that this is actually correct. Let us compute the right-hand side and make sure that we get the vector u. The vector v1 was 1, 2. The vector v2 was -1, 4. So -5 over 6 times vector v1, 1, 2, plus 13 over 6, vector v2, which was -1, 4. And let's see what we get. The first entry is negative 5 over 6 plus negative 13 over 6. That's negative 18 over 6, which is negative 3. The second entry, negative 10 over 6. 13 times 4 is 52. So we get negative 10, negative 52, negative 62 over 6. Oh, sorry, negative 10, sorry. Negative 10 plus 52 gives us 42. 42 over 6 is positive 7. There you go. And this is, as we had hoped, vector u. So there you have it. We have expressed vector u, negative 3, 7, as a linear combination of v1 and v2, where u was negative 5 over 6 v1 plus 13 over 6 v2. And you see whether you had vectors in R2, R3, or Rn for any n, and any number of vectors v1 through vm, you would end up solving just a slightly larger system, but that's the only difference. Let's do one more example to show you what we have in mind with this idea of linear combination. The idea will be to take objects, whether they're spaces, lines, or planes, and try and simplify the objects with just a few vectors. And a great example of this is a plane in R3 passing through the origin. And this will be the last example of this video. So suppose we have the following plane in three-dimensional space, given by the equation to go with x minus 3y plus 4z is equal to 0. Now clearly this is a plane passing through the origin because the point 0, 0, 0 is a solution. This is a plane passing through the origin. And now we're going to ask, can we express every single point of this plane as a linear combination of a few number of vectors? Because we know that the plane, being an infinite flat surface, contains an infinite number of points. And what we'll do here is we'll simplify this infinite set of points to, as you will see, two vectors. Well, if we want all the points on this plane, the points on the plane given by x, y, z are the solutions of this equation. So let's solve the linear system. And as you can see, I've picked an equation for the plane to give us a trivial linear system. It already is fully row reduced, so we can write the solution set. Y and z are free, so you can let y be s, z be t, and then solving for x will give you 3y, which will give you 3s, negative 4z, which will give you negative 4t. And you see your s and t are parameters. They can range over all real numbers. So we have just parameterized this plane. The points, x, y, z, on the plane have to have the following coordinates for some choice of s and t. Let's see what we can do from this. Again now, we won't write the points on the plane as a triple, x, y, z of real numbers, but as a column matrix of length 3. So x, y, and z, the points on the plane, must be given by these equations. So x must be 3s minus 4t for some choice of s and t, y must be s, and z must be t. And the question is now, how can we go from this single point on the plane to a linear combination? Well, we have here two free variables, s and t. Let's split them up. Let's do s times, well, what are the numbers multiplied by s? It's s times 3, s times 1, there's no s here, so this will be s times 0, plus t times, well, negative 4 times t, so negative 4. There is no t here, so t times 0. 1t, 1. And if you double check, you can add these two together. You'll get 3s minus 4t, check. S plus 0, check. 0 plus t, check. And now look what we've done here. Every single point on the plane is some multiple of the vector 3, 1, 0, call that v1, plus some other possible multiple of the vector v2. And if you look, this is a linear combination in the vectors of the vectors v1, v2. Take some multiple of v1 plus some multiple of v2, and you will get a point on this plane. And s and t range over all real numbers. So as you let s vary over all real numbers, same thing for t, this linear combination will allow you to get every single point on the plane. So we have expressed any given point on this plane as a linear combination of these two vectors. And let's visualize this graphically and why two vectors should not be surprising. Because if you think of it, a line is a one-dimensional object, so a line will be generated by one vector, but a plane is a flat surface, is a two-dimensional object, so it makes sense that we would need two vectors to generate every point on this plane. So you can visualize it this way, and again, I will not sketch an accurate picture of this plane in the three-dimensional coordinate system. I'll just draw a generic plane. The plane does pass through the origin though, so imagine this being the origin, 0, 0, 0. And position vectors v1 and v2 there, and you can see the vectors are clearly not parallel. Suppose this is v1. And the vectors are also not perpendicular. If you dot v1 with v2, you'll get negative 12 plus 0 plus 0. So the vectors are not orthogonal. Suppose v2 looks like this. And there you have it. You see, every point on the plane can be obtained via a linear combination of these two vectors. You can kind of imagine it. If you add the right multiple of v1 to the right multiple of v2, you can get any given point on this plane. So in a sense, what we've done here is kind of great, because the plane consists of an infinite number of points, and what we have done is we've taken this infinite object with an infinite number of points, and we have reduced it to two vectors, the vectors v1 and the vector v1 and v2. And this is the idea of linear combinations, trying to simplify these infinite objects. You have an infinite flat surface, there are an infinite number of points, but as long as you have these two vectors, you can build any point that you want on the plane by choosing the right multiple of v1 and the right multiple of v2. So think about why this is again nice. We have reduced a set of an infinite number of points slash vectors, because vectors are points and points are vectors, to 2 points slash 2 vectors. And this is quite a simplification.